Okay, so maybe I'll start with introducing our today's speaker, Professor Eun-Ah Kim. So Professor Kim got her PhD degree in 2005 from Urbana, and then she spent 3 years as a postdoc at Cornell University, at Stanford University. And then starting with 2008, she has been a professor at Cornell. Now, she worked on a very broad range of subjects, and she got many distinctions. For example, she is a fellow of the American Physical Society, and she was selected as a Simons Fellow. And I remember that when I first met our today's speaker, it was in 2006, and she came to Santa Barbara with a very interesting talk about interferometry in the quantum Hall effect. And so quantum Hall effect was one direction of her research, and that was the direction I followed particularly closely. But over the years, she worked on a very broad range of topics that goes from a topological method to high TC superconductivity. And one very special thing about our today's speaker is a very broad range of methods she used, from advanced analytical tools to various numerical tools. But more recently, she entered a field with a particularly unusual set of tools. So she is now using big data in the problems of condensed matter physics. But of course, she is not using them the way computer scientists would use the data. So today we'll see how big data works for a physicist. So let us welcome our today's speaker.
Thank you. That was a very generous introduction. Thank you for the introduction, Dima. I'm very pleased to be here and to tell you about some of the efforts that my group have been taking on, trying to harness data revolution in quantum matter. After some more pedagogical and for general audience introduction, I'm going to focus on two specific examples that you can find more details in in the in this let's see, in this paper and in this paper. Okay, so the condensed matter community have for many decades really wanted to understand how, say, different structures lead to these markedly different properties, and how certain materials exhibit very astonishing properties. And there is a academic interest or intellectual interest of wanting to understand, but there's also interest of by understanding we want to control. Now, the information content in our solid state materials, for instance, I'm showing here a crystal of cadmium rhenate, cadmium rhenium oxide. This is a relatively big unit cell with many atoms inside a unit cell. But if you have a perfectly ordered crystal, and if you are only caring about the location of atoms, the information content is it is intensive. It's not very big. It's about hundreds of bits. Now, however, if you take the all the defects, all the distortions that can be present, fluctuations, charge, orbital spin information, the information content can quickly grow. When the information contents become extensive in a piece of material, the amount of information can easily exceed the total amount of information in the Library of Congress. So although the community might not have been thinking in this particular light, in retrospect, you can think of all the efforts to try to develop new tools, new way of doing experiment, gaining more precision, all those efforts to be driven by the desire to extract more information. Now, out of those efforts, we've reached the stage of living in the era of data revolution. For instance, quantum systems, such as this IBM Q shown here, are now starting to be able to produce operate qubits of 6, 7, openly accessible to anybody, and up to 60. Now, there are still a lot of issues in terms of their noise level and so on, But now with this physical systems, there is a great desire to try to characterize them, assess them, and try to do things with them. But the characterization requires measurement. The very nature of quantum system is that you cannot know what you have. So you only can access the system through this snapshots of partial measurements. And then you want to reconstruct what state the system is in. And the Hilbert space that you're operating in is enormous. Another example that I like to show is the notion of tunneling density of states. In 1962, the tunnel junctions were macroscopic. So you have this tunnel barrier, and you have this macroscopic tunnel barrier, and you measure the tunneling conductance. And you plot one curve because at each voltage, you have one number. So this curve, which is really well known and loved by anybody who's been involved in study of superconductivity, when it is one curve, we've been able to understand it. There was one curve thrown to the entire community, and we've been able to understand why there's a suppression of the density of state, why there is a peak. Those are very salient, standing out features, but we were also able to understand why there are these little bumps and wiggles, and being able to reproduce that from a simple model gave us a sense that we understand what's going on. And that's the BCS theory, success of the BCS theory of superconductivity. Now, fast forward to 2000s, instead of having a macroscopic tunnel junction, now we have tunnel junction at atomic scale. There's a small space, tiny space of vacuum that forms a tunnel junction. And now over a surface of the sample, there are many, many such junctions. And as you move the probe around, you have, instead of a one curve, you have as many curves as the number of points where you've taken the measurement. So now you have this kind of three-dimensional data. It's not just STM. Many different probes have moved on to scanning mode. And the desire is that if we get more information out, that would mean that we understand better. However, if you open famous any standard textbook, say Ashcroft and Mervyn coming from Cornell, you would not find how to interpret this kind of data. You will not find the guidance on how to interpret this kind of data. X-ray diffraction, another very sort of a fundamental probe of study of solid-state systems. In 1913, this paper by father and son, Bragg and Bragg, in Proceedings of Royal Society, which eventually led to Nobel Prize, made a great impact in the community by presenting the very first successful forward modeling example. They said, okay, as I tilt the angle of my sample, I see these peaks. They have 3 peaks, and they came up with this model that if I have a lattice of atoms forming a regular lattice, I can think of an interference condition, which would lead to this formula explaining that from the peak location, I can read off the distance between the planes of atoms. Of course, we learned this now. It's well accepted, very impactful, to the extent that we learn this, teach this in introductory physics. However, this was the very first example of successful forward modeling. The volume of the data have increased now tremendously. So this is, let's see. This is a slide that I've taken from my collaborator at Argonne National Lab. He's showing that as you rotate the sample, everything's automated. And these little cells here are Brillouin zones. So now you're covering many, many tens of thousands of Brillouin zones, which means you have much larger volume of data. Moreover, your dynamic range of your detectors have improved. So you have much more detail than just here is a peak. So in my group, over the course of last couple of years, we've been pursuing the idea that we can let's try to use data science tools such as probabilistic modeling or deep neural network to gain insight from rich, vast, complex experimental data to arrive at theoretical insights. And sometimes, hopefully, you can do it faster than what it would take a human researcher to do, so that you can give kind of real-time feedback to the experimental setting. In this direction, we've worked on many different types of experiments and many different types of data. Speaking of quantum systems, recently we posted a paper where we were importing tools that are developed for natural language processing translation to do the quantum tomography used on the real IBM system data, IBM-Q data. This paper was our first, and I think the community's first example of applying machine learning tools to quantum matter data, real experimental data. This was looking at STM data. In this paper, we looked at resonant ultrasound spectroscopy, which is a spectroscopic tool which have been always analyzed through a reverse and inverse problem. Here we looked at non-Fermi liquid transport in a quantum critical regime from simulated data. This is synthetic data, but data that needed to be nevertheless mined because data is in imaginary time. What I'm going to focus on today are these two work. The first one is using a tool that we called X-TEC. It stands for X-ray diffraction temperature clustering, X-ray temperature clustering. And the second is looking at quantum gas microscopy, trying to gain insight from using inherently interpretable neural network whose interpretation is built on notions of correlation functions. Like Dima said, I think the fact that I am doing this, I'm in this business of trying to use data science tools, came to many people as a surprise. But it came out of sort of introspection. Okay, so introspection goes as the following: as physicists, we love to look at some nature. We are scientists. We look at some phenomena, and we love to understand. And what we mean by understanding is being able to talk about it in some simple, coherent, logical principles. But when there are multiple ways of thinking about things, we look to the judgment of the nature by saying, okay, this is my falsifiable prediction, and see if I can predict what's going to happen. This same mode of science is not only limited to physics, and when this mode of operation is used with the data science tools, going in the understanding direction, coming from complex reality of data to simple principles, is called regression. Trying to model what's going to happen based on your ideas priors is called generative modeling. So the thought is, well, if this is what other people are doing too, maybe some of the tools that they have developed can help us. The big challenge in using the tools to make meaningful contribution to science, especially physics, is the fact that the physics is a discipline that is very special by having the long heritage history and a very well refined mode of thinking. So the only way machine learning tools can contribute to progress in physics is to be able to interpret what you're doing within the language of physics. We need to be able to bring back what we learned with machine learning tools and interpret it within physics. And when you try to do that, one of the things that I've learned is that I look at various tools as tools, like the one I'm showing here. So this is a fantastic tool, industrial grade blender. It's a fantastic tool if your task is to make a smoothie. All tools are very task oriented. But if your task is not to make smoothie, but to make guacamole, this is a better tool. Even though this looks like a less developed tool, this looks like, coming from Stone Age, but it's a much better tool for making guacamole. Why? Because you can see the ingredients and you can savor the flavor. It goes the same way with physics. When you use a simple minimalistic tool, which allows you to see what is at play, then you can find that optimum point between using the tool and gaining convenience and speed, but at the same time, being able to put it back to your language of physics. So the first topic that I want to talk about is XTech, XRD temperature clustering. And this is unsupervised machine learning tool for voluminous X-ray data. It was really spearheaded by my two graduate students, Jordan Vandely and Michael Meddy. But real fun was also in that we got to work with people coming from very different disciplines. So my colleagues at computer science and staff scientists at CHESS, Cornell High Energy Synchrotron Source, and scientists at Argonne National Lab. And in this paper, we have huge list of authors. And I don't think, except for my graduate students, I've never written any paper with any one of them. It was a whole new, fresh collaboration. And it's one of the fun side of doing what I'm doing now. I get to meet a lot of new people and new perspectives. Okay, so what are you trying to get out of X-ray data? If I'm interested in emergent phenomena ordering, I could be looking for charge density wave or intra-unit cell order. So charge density wave is starting from, if this is my fully symmetric one-dimensional crystal with 2 sites per unit cell, charge density wave changes the unit cell size. For instance, here we have charge density wave of period 2 because of these distortions. And you can see if this is what's happening in the real space, what we get to see on the X-ray side is the emergence of this superlattice peaks. Now you see that there is also a different sort of intensity increase as you go to outer zones. That's what happens with charge density wave. You see this new superlattice peak show up. Now, intra-unit cell order is symmetry breaking that does not change the unit cell size. Without the change of unit cell size, you will not get new peaks at non-integer locations. But this obvious symmetry breaking, if you could see in the real space, is reflected in the X-ray data through these subtle changes in the form factor. So now comparing this side to this side, you see the impact of this ordering, which is inversion breaking, was in the height of these regular Bragg peaks. So this can be much more subtle to detect because it's not giving rise to a new peak. So now the question is, how do you detect these subtle changes when you have, instead of 3, like Bragg and Bragg had, 100,000 peaks? If you are looking at this large volume, how do you search for a special Q? Now, speaking of the pandemic era, I had different kind of volume problem. And this was my pandemic parenting volume problem. I've been asked too many times by my kids to go find that special piece they need to make something that they're trying to make. And you quickly learn, within a couple of tries, that picking up one piece and inspecting, is this what I'm looking for? Picking up another piece is a really bad idea. Our attention span, you quickly discover, is very low, and you cannot stay alert in this repeated operation for more than 5 times a repeat. So you miss things, even if it was blatantly in front of you. So what we learned, us parents in this household learned, is that what you have to do is actually sort. So if you're looking for a yellow piece, after you first sort, you just have to look inside the yellow bin. Maybe shape is a better way to sort depending on the piece that you're looking for. Now the question is, if I am looking at X-ray data, not Lego pieces, what should be my sorting criteria? My peaks do not come with color or shape. So what should be my sorting criteria? But some way of sorting seems to be a good strategy. What we came up with is that, well, these free amplitudes of density, the intensity, has temperature dependence. Or if you have some other parameter, you would have dependence on your control parameter. What the control parameters do is that they enter in free energy to give you the balance between what's inherent in the Hamiltonian and what is the rule of entropy in the case of temperature. So when the inherent interaction that contributes to energy starts to win over the entropy, you start to see new things emerge. So the idea was that, well, then we expect different temperature trends for different groups of intensities at different locations in Q. The idea was to literally think of different points in reciprocal space as population. As we are thinking a lot about populations and their voting, their political leanings these days, we are looking at the population of our reciprocal space points. So now let's look at the data, see if we can just figure it out. Do we need to go to machine learning? This is a titanium diselenide data, which is a well-known charge density material. And if you know where the charge density wave peak is, that is where the superlattice peak is going to emerge, you can make a cut in that plane. And if you were that intelligent going in, of course, this is not something that where you will learn something new. But you will see like these peaks disappear as you heat up beyond the critical temperature. This is a half integer point plane, so there are no Bragg peaks. So what does it look like if I didn't know, and if I just was facing a bin of this curve, this intensity trajectories as a function of temperature? What does it look like? And this is what it looks like. Although there in this huge volume, there must be a collection of intensity trajectories as a function of temperature that's showing an onset behavior. You can't see it, it's buried. So what we first had to learn was, this was Jordan's idea. Jordan realized that the huge scale, the dynamic range between this is, it's hard to see, 10,000. 10,000 was still not enough because Bragg peaks are really bright. My my sensors, detectors, dynamic range is large enough. It had this, huge dynamic range. So what we first learned how to do is to employ sort of a principled procedure to threshold and remove large scale noise. And that leaves us with this. Jordan's rationale was that, look, I have a grid of Q points, but in most of this space, it is there isn't much information. It is very sparse. So let's try to reduce the number of Q points that we have to look at. So then that leaves us with this pre-processed data. And then the actual machine learning strategy we employed was inspired by how one would do speaker verification in sort of early stages of speaker verification. When two people are speaking in the room and you have one of these AI devices, you will notice that the device can tell your voice from, say, your partner's voice or your children's voice. How do you tell apart when you have multiple voice trains that are mixed? One of the strategies to learn some characteristics in that voice train that separates the two, and that's not necessarily Fourier transforming, but just learning the different characteristics. So a similar approach that we took was the basic approach we took was called Gaussian mixture model. So what we are now going to do is to take our pre-processed temperature series, which means I have for each position in Qi, the number of temperature measurement points, number of entries that's forming a vector, and that's my trajectory or temperature series. And the starting point is to conjecture there being some cluster number of, let's say K, distinct multivariate normal distributions. So if I have a normal distribution, ignore all this normalization. If I have a normal distribution, I would have means and I will have variance. So if I assume a particular mean and variance for my normal distribution, the conditional probability that my data point actually came from that distribution is nothing but this Gaussian. Plug in the value of your data. I think a parenthesis is missing for where you put x minus mean. And then you have this log likelihood because we've assumed multiple such normal distribution. We say, okay, my data train can belong to one of these normal distributions with a weight pi of k for that particular one. And then we optimize and learn these parameters. The weight, means, and variances of each cluster are hyperparameters that we learn using expectation maximization principles. Once we learn these parameters, we have the cluster assignment. And this whole process for terabytes of data can take only a matter of 10-15 minutes. Okay, so after developing the tool using titanium diselenide data as our guinea pig, we applied this to a new data set that's never been looked at before, and that was a data set on pyrachlorocadmium rhenium oxide. It's a material that's known to be the first pyrachlor superconductor, which excited researchers in the field, but it also has structural transitions. So superconductivity emerges at this low temperature out of one of the lower symmetry structural phase. Obviously here there is singularity showing there is a second order transition. The structures of the high temperature phase is well understood as a cubic phase, but the lower temperature phase obviously would have lower symmetry, but there are many options because cubic phase is a very high symmetry phase. In this work, higher harmonic generation, second harmonic generation was used to claim that the phase transition here has the order parameter for that phase transition has one-dimensional T to U character. And what's been typically viewed as possible ordering route was really a secondary phase. So the goal was to try to see whether something was missed, or rather to study any structural transition possibilities, making sure that we don't miss anything. That's where the idea of looking at large volume of data came from. So my colleagues at Argonne National Lab took about 8 terabytes of data spanning 15,000 Brillouin zones. And this is the result. And if I didn't tell you this is a result of, if I didn't tell you all this, you probably wouldn't have guessed that there is, you know, half of Congress, a Library of Congress in here. What is being plotted is the mean that was learned, and the range is the variance. So this is a machine learning tool that tells us how much we can trust this result because it gives us the uncertainty, the variance. And the interpretation that I've emphasized is immediate because you can just look at the mean and see whether it behaves in any way that you would have anticipated. So you see something that's looking very classic order parameter looking. Now this is a transition that is intra-unit cell. There is no unit cell size change. So this is not a matter of new superlattice peak showing up, but when the symmetry changes from high symmetry to lower symmetry, Bragg peaks that were forbidden by symmetry can appear upon that symmetry lowering. And that's where what this is, which you can tell not by just looking at this, but by looking at where the population came from. So these votes all came from these counties, the purple counties here. And you look at the purple regions and you realize, oh, those are all HKL with one of the HKL being 4n plus 2, which indicates one of these two possibilities, I4 bar M2 or I4 bar. These are the lower symmetry possibilities for this phase. Now you see that the reciprocal space mapping is very simple. That's because for this stage, we've treated all the reciprocal space points around each Bragg peak to be just one group. Now, in order to gain better understanding of what's happening at lower temperature, which you hardly can see in this clustering, we opened up each of these counties and went into individual level. How did you vote in your county? So when we did that, we learned that we have to use 4 different clusters instead of 2. So what we typically do is we change the number of clusters until we see the number of clusters do not cause any changes to what we can perceive. And in this, when we opened up the whole data set, we needed to use 4 clusters. 2 was not enough. More than 4 was more than necessary. So then we try to look at where are these 4 clusters coming from. Supposedly there were 2, whether you were now allowed by symmetry at a lower symmetry phase or not, and where are these all 4 coming from? Now, blowing up, we learned that centers of all the peaks were showing relatively mild temperature dependence well below the transition at 200 K. So centers of peaks were all showing relatively mild temperature dependence. They have turned on, and there wasn't more change being detected. But different cluster assignments came from the diffuse region. This is a halo around each Bragg peak. This is a region which can or may not have intensities, because we are just coloring the region like you color the map. So in order to figure out what is going on, we looked at the raw data, and we find in these red clusters, there is extra diffuse intensities all throughout this phase 2 over here. That's the red region. But in the blue region, there isn't so much of, compared to the red region, much weaker diffuse intensity, which becomes a little more pronounced below in the vicinity of the lower transition. We got to this point more or less within hour or so of since we first received the data, and that's when we started to get really puzzled. I talked to my colleagues at Argonne and said, look, the diffuse region is being clustered into something separate, and they wouldn't believe me. They would say, like, no, you cannot really learn a whole lot from the diffuse region around Bragg peak unless you're looking at critical fluctuation, and this was not critical fluctuation. The critical point was up here at 200 Kelvin. Eventually, after 2 months of getting puzzled about this, we realized this enhanced scattering in this whole region is consistent with the order parameter being 2-dimensional, being under weak symmetry breaking, weak anisotropy, in which case you would have Goldstone mode fluctuations. And this, where these enhanced diffuse scattering effects were being seen, was informing us that this Goldstone mode fluctuation, which is allowed in I4 bar M2, one of the candidate structural phases, involves specific motions of the atoms, that cadmium and rhenium moving in antiphase, fluctuating in antiphase. And this level of detail was, this was first instance of being able to learn that level of detail at atomic scale, which was in principle possible given the volume of the data, but there had not been a tool that's meaningful to look for this. So now I'm going to switch my gears and move on to the quantum gas microscopy. But before I switch my gears, are there any questions?
Hi. I was trying in one of the previous slides where you showed the intensity variations with temperature, and the variance was like the region around.
Yes.
So this kind of looks like it looks like an order parameter.
Yes.
Which you'd see in the intensity, but you'd also see at a second order phase transition a correlation length diverge.
right?
Kind of looks like the 1 over the variance
Mm-hmm.
is diverging. Is there any relationship between this variance and?
That's a good question. I haven't thought about that. There could be. There could be. Yeah. So this variance is what's coming from our, let's see if I can, sorry to be, yeah. So variance is one of the hyperparameters because we are using Gaussian. So we're sort of guessing that the data can be captured by some Gaussian distribution. And mean is the mean of the Gaussian, and variance is the variance of the Gaussian. And it's really saying that my data more or less follow this trajectory, but there is this much variation in the intensity. Now, in saying this, because each Q points are treated independently, there is no spatial information in this. There is no Q space information, there is no spatial information. But perhaps the fact that the intensity variation becomes tighter upon turning on, perhaps is related to that. That's a very interesting point. I think we'll have to look more into this. Thank you. So short answer, I don't know, but that's a very interesting point that it's my homework. Any other questions? All right, if not, I'm going to switch gears. So now correlation CNN. CNN stands for convolutional neural network, and correlation CNN for quantum images. This work was done in collaboration with a group at Harvard, and it was really led entirely single-handedly by my graduate student Cole Miles, who was supported by DOE graduate fellowship. Okay, so Fermi-Hubbard model, a famous model that's sort of poster child model of strongly correlated systems. And one of the reasons why people would like to understand this model better is because it could be something that's important for understanding high TC-cube phase diagram. The experimentalists working with ultra cold atoms have finally reached the temperatures. Ultra cold atoms finally became cold enough to see antiferromagnetic fluctuations and also perhaps the strange metal regime. But what's really lacking is that this is a system that's not a solid state system, and the way to study the system is also not the way we study solid state systems. Specifically, you study these systems using quantum gas microscopy, which gives you a projective measurement. It gives you a snapshot, much like how the measurements of quantum systems work, like at quantum computers work. So it's not giving you the ensemble average expectation value, but it gives you snapshots. You can take many snapshots, but that snapshot is what you get. So now there's a challenge of, we worked hard to emulate the Hubbard model that cannot be solved exactly with because of the sign problem, and we can even take data, but we don't know how to interpret it. Of particular interest is trying to understand this so-called underdog regime, where you're introducing holes to the antiferromagnetic background. And we were interested in testing out two specific conjectures. One is the idea of geometric string, the other is a pi flux theory with singlet bond. So pi flux theory is an idea of starting from resonating valence bonds, and that you introduce the holes, and holes will kind of move around freely with the RVB background. Geometric string idea is sort of a frozen spin approximation, saying, okay, the spins mostly stay frozen, and you introduce hole, and as that hole tries to move, it's going to have a wake of bad bonds behind it. Both are plausible ideas among many other ideas, and what these ideas share in common is that they have to interpolate to antiferromagnetic order in one limit. So when you dope a little bit, they all look pretty similar. It's hard to tell them apart using sort of conventional measures such as magnetization or correlation function, a two-point correlation function. Earlier, there was an effort to use off-the-shelf CNN using TensorFlow to build CNN that's easy to build. Problem with those that were designed to do the image recognition, being able to tell where my hairline is, level of image recognition, is over parameterization for my essentially black and white dots data of so many pixels, pretty small, and it's also a black box. Nonetheless, quantum gas microscopy is the tool for studying this ultra-cold atomic gas systems. Many groups are implementing it. So the idea was that let's try to develop a tool that builds in interpretability in a way that we can interpret in the language of physics. So to describe how our correlation CNN works, let me first give you some sense of how convolutional neural networks work in general. This is CNNs. So convolutional neural networks, you take image data and you have a convolution filter, and you make a convolution map. That's a map going from the data to a new set of pixels, where the convolution map works by taking a convolution with the filter. So when you change the filter, the map is going to change. And what you do with CNNs is that you try to learn the filter that gives you the best expected results on your training data. What you have to do after making convolution is often there's pooling, which is about reducing the data volume, but then the crucial step, whether you have pooling or not, is non-linearity, which gives you expressibility. What my student Cole realized is that when you have off-the-shelf non-linearity, such as tangent hyperbolic or step function, it's very hard to interpret what that means. But if we take the convolution, like here, and when you look at higher order powers, for that amounts to introducing correlations of that order. So he thought, like, why don't we, this animation, credit to Cole is hard for me to, oh yeah, okay. Yeah, so this is what the first order convolution does. It just looks one pixel at a time. Second order convolution, because when you square it, you're picking up 2 points in the data. Which 2 points you pick up depends on which filters you use. So you're picking up different sets of 2 points in the second order. In the third order, you'll pick up 3 data points or 3 pixels from data. And again, the filters that you use will determine which 3 pixels you are picking up. And as you move the filters, this will also change. So Cole's idea was that if we use order by order nonlinearity instead of off the shelf, then we'll be able to, and if we figure out which order mattered, we'll be able to interpret by saying, okay, this correlation function was important. So this is the correlation CNN architecture. We take the quantum gas microscopy data, we spin up, spin down, and holes, and we convolve it with the filter. We have the convolution result, and then we take powers, and then each of those are averaged to give us 4 numbers. In this case, if the number of as many numbers as the number of correlations that we're looking at, and then we put it through the logistic regression. So this is what we do in a training stage, training with the 2 labeled data set, labeled for 2 of the conjectures hypotheses that we're testing, which is geometric string and pi flux. Once we are done training, in order to figure out what did the CCNN learn through the training, what we do is what's called regularization path analysis. So we fix the filters, hold the filters fixed, and then taking only this logistic part, we put in the new loss function. This is a loss function that penalizes trying to have weights on the input data. So the balance between the penalty coming from this lambda and that input helping the decision, correct decision that we reward will show up in this kind of regularization path curves. So as you ramp down beta, when lambda is really, really big, you don't want to have any weights at all. So and by not having weights, you haven't learned anything and your accuracy is bad. As we ramp down lambda, so going this way in the log lambda plot, as we ramp down lambda, different inputs that came from the correlation starts getting turned on. So looking at this branching, we see, oh, for this filter's fourth order, this for the filter which was fixed, at the fourth order, when the fourth order correlation was turned on, we gained this much accuracy. And this other fourth order correlation was turned on, we gained this much accuracy. So we gain pretty much all the accuracy we need by turning on fourth order correlators associated with two filters that we used. And then that revealed to us fourth order correlators are important for this, which is not typically what we think about. So then we could further look at what the fourth order correlator, because we have physical meaning to this nth order correlator as collecting n number of pixels. What's the fourth order correlator filtered by this particular filter mean? Now we can just look at collection of the filter weights because the filter was already learned. And we see, okay, so this is one, and these are different configurations that you can pick up by looking at fourth order correlator, which is to choose 4 pixels. And then now we can stare at this and see, do they seem right? Are they something that we physically anticipated? And what we see is that the patterns that are showing up are exactly what you would get when you have a wake behind a hole moving in the antiferromagnetic background in the geometric string picture. So this was the right filter to learn with the fourth order correlator to learn the geometric string. And we figured out that the CCNN indeed learned that, which was a sensible thing to learn. And for pi flux, repeating the same thing for the filter that was designated pi flux, we do the same thing, and we see that it's learning fluctuations around antiferromagnetic pattern. So this informed us, first of all, these fourth order correlations are what's important, which was not known until this point. This informs experimentalists on what is it that they need to know, what information is necessary to be able to discern their data against some hypothetical ideas or pictures, proposals. And it also, we were able to use this to also tell whether the CCNN trained on the simulated data was able to pick up the right information from experimental data. Because our data is much more expensive compared to the everyday life data, we do not have the luxury of training with some database repository of data, which anybody learning do machine learning first learn to one of the things that one could do is to learn to recognize the handwritten digits, because there's a data that's available for you to go play with. We don't have that luxury. Those handwritten digits are real. We don't have the luxury for the real data. So often people try to simulate data and train on the simulated data and give the real data to the neural network that was trained on the simulated data. And what we hadn't known how to assess when we go through that process, which I myself and many others have done, is that whether the neural network learned whether it was generalizing to the experimental data. Like, simulated data has a lot of artificial idealized features because we can only get only so much complexity with when we figure things out, when we write it down by hand. So if there is something that's different about the experimental data, is a neural network obsessing over those meaningless features, or is it obsessing over what is meaningful? That is hard to know. With CCNN, we were able to try this on real data, which did not have spin resolution. And we learned that by not having spin resolution, there was uncertainty in the actual hole density, and that meant this exercise wouldn't go through. That was information that was critical, because if that is wrong, that's low order process, and that's what the only thing that the neural network got obsessed about. So let's see. So to summarize, I described two specific examples of XTech, X-directed temperature series clustering. Although we say temperature series, I think the approach would hold for any kind of control parameter. It could be pressure, composition. When you have a series that can form a trend that gives us a large dimensional vector that we can try to model with the Gaussian mixture model. This can be a very broadly applicable tool. We are currently working on implementing it into making it part of the facility at Argonne National Lab and CHEST. The idea is when the researchers, the mode of operation today is for people to write a proposal for a beam time. They do experiment at the facility for a week, and then they go home. They log into the facility server for the next 6 months or so, try to figure out what to make of that data. And maybe they will discover, gosh, I should have taken data point at one, a few degrees higher or a few degrees lower. I should have taken more data points around here. And then you have to repeat that process, which simply do not have. Our graduate student time is way too expensive to look at every single data point that you acquire that way. So only a fraction of the data gets inspected and the rest gets thrown out. The goal is for this tool to be part of your measurement, so that you take your data, go for coffee, come back, and you look at your XTech output and see whether there was something meaningful in your measurement. And then you can change your measurement setting if there wasn't something meaningful, or maybe there's something that you want to study more, you can dig in more. CCNN, correlation convolutional neural network, more and more data, more and more measurements are are going into a scanning mode. And for this image-like data, when we cannot turn to trustworthy textbooks to figure out how to analyze them, we believe CCNN can be actually very helpful way of analyzing this data. And in closing, I want to close on this slide. This was taken from this wonderful movie called Hidden Figures. If you haven't watched it yet, I highly recommend it. This is a scene towards the end where Dorothy Vaughan, who was the leader of West Area Computers, the colored computers, and these are human computers before we had machine computers. Some of the computers at the time lost jobs. They were replaced by the machine, gigantic thing that used up big room, which was not as powerful as my iPhone, but still it was more efficient. However, these people didn't lose the jobs as computers, but they became programmers, because Dorothy Vaughan had the vision to learn this newfangled thing called Fortran. And they were able to program this machine, and operate at a higher level than the machine. Machine is a tool, but if we know how to use it, we can use it for our purpose. So that's what I like to say when people question, will machine replace physicists? I don't think so, but I want to be at least ahead of the game. And on that note, thank you very much for your attention.
Okay, so let us thank our speaker. And any questions? So I guess people who cannot unmute themselves, perhaps it was suggested that maybe a good idea to type questions in the chat. But I think some people can unmute themselves. So if there are questions. So now everyone can unmute themselves, right? Okay, so maybe I ask one question that actually is quite close to what you told at the very end of your talk, but it relates to its first half.
Okay.
So the story you described to me reminded me perhaps the earliest and very famous example of the use of big data in physics some 400 years ago. So back then, of course, we did not have much data, but there was one exception. That was astronomical observations which were accumulated over thousands of years. And already by that time, the data about the motion of the visible celestial bodies was enormous. And for centuries, people were trying to make sense of these data by inventing trajectories which were combinations of circles. And every new piece of data would require an additional layer of the circles. And so the system became insanely complicated. And then Kepler comes and concludes that adding another layer of circles is too much. And realizes that we should look at the motion of the planets in a completely different way than what people were doing for 2000 years. And now if I compare this with your stories, and you got your big data that showed you some strange anomalies, but then it was human thinking that finally led you to a conclusion of what's going on. And this leads me to a question. What do you think? To what extent, clearly not the current computer technology, but the future technology may participate in that second half? So do you think that we will eventually get computers who will perhaps not be Keplers, but would do certain things that humans normally do? Or you think we are still on the trajectory that just extends quantitatively the sort of big data that was actually available for thousands of years in different formats?
So that's a question of whether the machines can really become intelligent like human, or and that but there's that's a big tent, but there's a specific question, I think, of when what's really unique about human way of thinking is we like to see things simple. We have a desire to find a simple way of looking at things. Like the example of Kepler was trying to find something that is simple, and there's perhaps the way how our brain works. And there are cases where that desire for simplicity have really led to more powerful discoveries. Currently, the machine learning tools are not designed for that. Nobody thought to put emphasis on trying to make the algorithm that can come up with new theories, new ideas, new simple, and the emphasis on the need for being simple. But I don't think it is impossible, but that's not what's developed. And left to the computer science community, they probably won't develop that. So if that's what physics community desires, I think that's something that we have to figure out. I don't know whether that answers your question.
Well, no, thank you. I don't think that is a good answer to my question, but
Yeah.
thank you for the way how you put this. Now, I think Sean has a question on the second half of your talk. I think Sean is unmuted, so he can ask the question.
Hello?
Okay.
Can
Hi.
you hear me? Hi,
Yes.
for some reason, my office video doesn't work. So, so I'm going to go dark here. Okay, so on the second part of your CCNN, I don't quite understand what's the question. So, okay, so my understanding of this underdoped regime to represent the whole doping, the geometric string or pi flux, there are just different ways of writing down the wave function for the holes. And then so as we know, we can always in quantum mechanics write in different bases as we want, right? So as a result of these two bases, the physics should be identical, right? So in your learned correlation, I don't get what's the what you are trying to what's the end result here. I don't understand what's
right. Okay,
what's the
good.
question you try to address.
Okay. Yes. So the question was, if let's not think of it as geometric string and pi flux. Let's say I have candidate description A and candidate description B, and I have image-like data. And I want to know whether my hypothesis A or hypothesis B better describes data. That's the question.
But they're equivalent representation of the same thing.
They are not, well, they are both wave functions that are designed to be a description of underdoped Hubbard model.
Yes.
But they are not, the inventors of each wouldn't say they are the same. But both are kind of featureless. But one is coming.
In the end, you're looking for the matrix elements, right? So are you saying your method can find the matrix elements that you would otherwise have a hard time finding it?
I'm saying the what the neural network does is that it learns, maybe I went too fast there. It learns based on the label data set. So we simulate data based on each of these hypotheses with variational Monte Carlo.
Can you go to the slide where you defined the convolution?
Yeah. So what we do is, what's not shown here is what's the training process. So training process is I generate the pictures that looks like the quantum gas microscopy snapshots from theories, from two different theories. Wave function ansatz is a theory.
Well, the two theories they just write down an ansatz, right? Basically,
right. So based on the ansatz, I can simulate, because if I have the ansatz, I can simulate the quantum gas microscopy. It's just Fox space snapshot. So I can simulate a snapshot using Monte Carlo. And I know that because I've simulated it, I know which one came from where. And I can train the neural network to tell them apart with high degree of confidence. So neural network, once trained, it would say with the 90% accuracy that this came from one ansatz and this came from another ansatz. It doesn't know how I made them up, but it learns what's unique about one wave function versus another. And then what we would like to know is, what did it learn? Because these neural networks are black boxes. And what we figured out is a way of putting our finger on, okay, this is what you base your judgment upon. And what the features that judgments were based upon turned out to be for this particular problem, fourth order correlation functions. That's what we learned. And that's not always going to be the case for different classification tasks. This is a classification task. And to differentiate these two ideas, neural network had to pay attention to fourth order correlation. And that's what we figured out. But the point is, this approach, this was applied to this particular data set and the particular ansatz to match up against each other. But generally, when we have this kind of image-like data, we're trying to see whether theory A describes the data better or theory B describes the data better. And in all such situations, this approach can be useful because you can train the CCNN with the simulated data, and when it is trained, you would know what it was basing its judgment on.
I guess what I don't understand is this: if I look at your C is a convolution function times your signal, and this awfully looks like the lock-in amplifier, and then it looks like the nonlinear element that mix up the mixer that's mixing up a signal with a reference, and then what you do is you filter out the high frequency component by passing through a low pass filter. So there I can see clearly how you can get rid of the noise. Here I don't see a way. I don't see you gain anything by doing this, because I don't see you. All you did was you multiply something you know. You did some.
No, we didn't. We didn't know the filter. We learned the filter. We didn't put the filter by hand. Filter was learned.
So I'm sorry, Sean. So I think so if you want to continue this discussion, maybe it should be in a different setting, because it's taking a lot of time, and we have another question from Camp, and honestly, I think that will be our last question, because.
Okay.
So Camp, maybe you ask a question.
Okay,
so sorry for interrupting, but
it's very interesting, but I'm not convinced that this is useful.
Well.
Okay, thanks, Eun-Ah, for a nice talk. I have a question actually about the diffuse X-ray data, or kind of that more broadly in terms of other experiments, because the diffuse X-ray scattering is kind of a special case where there's an embarrassment of riches, where it's very, very easy to collect a lot of data as a function of whatever parameter you want.
Right.
So what about applying this sort of stuff to other experiments where maybe it takes a lot longer to collect the data, so we don't have, I guess we might want to learn how to better do our measurements with a small set of data we have. I guess that would require a supervised approach, but
so
then,
yeah.
Then you might be biasing yourself because you
right. That's the danger of supervised approach. So CCNN was an example of a supervised approach. And my point is, if you want to do a supervised approach, which is sort of way to match up between multiple different theories, right? So you have one hypothesis, one conjecture saying I describe your data better, and another person saying I describe your data better. In that setting, supervised approach could give a more objective referee of which one of the theories actually describe the data better. Now, for analyzing data, but if you want to analyze data without bias, unsupervised learning is a better approach. And but it's not something that you can use all the time. So here, what I showed was an example of X-ray. Now, so to apply this approach does not require the data volume to be enormous. It's more that when you have a large volume of data and you don't have any other way of studying it, this is obviously a better way to do it. Now, generally, the way I think about it, if you have data set that you don't know, you don't have a good way of analyzing, right? And for the and if you have some control parameter that you're changing, let's say you're changing temperature, changing pressure, you're changing composition. If you have several data points, so what we need for this X-Tech approach to work is for there to be at least, you know, order 10 control parameter points, be it temperature or pressure or something, because you typically do measurement as you change something, right? Another place where this sort of approach might work is some sort of time-dependent measurement. If you do some time of flight measurement, and time-dependent measurements are also often very hard to model, and therefore try to extract information from it. If somebody gives you a time series, what people typically do is to Fourier transform to see if there is some peak that shows up. But Fourier transform is really good at finding something that's sinusoidal. If it is not that, it's not very good at figuring things out. So being able to learn sort of a trend in your data set, I think X-Tech kind of approach can be actually very helpful. And if you're asking what is the requirement to apply X-Tech, let's say, I would say in whatever giving you the trend, I want that series to be at least 10 data points long. And then the volume that I'm going to sort through does not necessarily have to be, you know, gigabytes, terabytes. We work with 100 kilobytes. And when we developed the tool, we actually developed the tool on 1 or 2 Brillouin zone of volume of the data. So I don't think we need the volume. Volume is not a necessary condition. Does that answer your question?
You need the control
Yeah, yeah, for this particular approach, right. So for this particular approach, we designed it around having a control parameter, the knob, and that gave us an angle to learn different qualitative trends without trying to do the forward modeling. Trying to forward model is expensive and it's hard to capture everything. But if you can capture a lot, it's also very informative, but it's very expensive. When we decided we don't want to do any forward modeling, we need something else as a way of learning what's in the data, what's the trend in the data. We're trying to figure out the trend.
Can I just ask a quick clarification? You mentioned that when you found the trend in this diffuse scattering, that you eventually recognized as this Goldstone mode.
Right.
But the experimenters kind of said, no, that can't be right. It's not that the data was recognizing, or the machine learning was recognizing something that wasn't actually there in the data. It was just kind of the human error of saying this is probably not interesting for some time until you figure out why it's interesting.
Right, because my colleagues were not used to looking at that part of the data. That they were not used to looking at it. So we figured out this Goldstone mode story together, because when I first said, look, my diffuse region is being clustered separately from the center of the peak, we first got to that point when we had like 3 or 4 pixels around, because we're looking at low resolution, many Brillouin zones. So when I have 4 pixels around the Bragg peak, I said 3 of them are one cluster and 1 is another. My colleagues didn't believe me. And I said, I know this 4 dividing between 1 and 3 is a very small number, but I have the number of Brillouin zones to give me statistics, and that's why I'm confident. But to come to believe in this and to gain better understanding, we had to do high resolution measurement. So what I'm showing here, that gave us confidence, first of all, that this is real, came from high resolution measurement. And once we had the high resolution measurement and seeing this in the line cut, everybody believed that this is real. And this line code looks very dramatic. And then we have to figure out what this is, because seeing a Goldstone mode fluctuation in X-ray data is not something that happens in everyday experience to my colleagues, because it hasn't happened before. So we didn't know to recognize it because people haven't seen something like this before. But what I'm really happy about what we've done with this XTech is, because I've worked with this and I know how it works, I know that it does not make up anything. It's just telling us what's in the data. I've not done anything to the data. I was just able to look at the entirety of the data and look at the trends and try to model the trends and figure out, okay, these are different trends in the data. And that's just really, really gratifying, like that we can look at this whole data.
Yeah, no, I know that's especially since you say you can do this now in an hour, because as someone who's wrestled for months to years with these sorts of data sets, it's it can be pretty enabling for people at beamlines.
Yeah, so we haven't done anything to the data. We just found where to look, and we look at what I'm showing you in this. What I've shown you was raw data, and only when we looked at the raw data, we believed ourselves.
Yeah,
and that's also very important. Sometimes we've seen something and we thought there is something going on, and then my X-ray colleague said, "Oh yeah, that's called streaking. That's the instrument issue. Oh yeah, there was some explosion. There was construction happening next door." So what we really need is back and forth. And when we can learn something new after learning some construction and after learning some instrument malfunction, and then finally learn something that's actually new, that's really exciting. And there was a lot of like reaffirmation that this is really a teamwork between some entity that has more patience and doesn't need to go to bathroom and doesn't need to sleep, and us who know how to think, looking for a simple insight.
It makes a very tight feedback loop.
Yeah.
Right.
Yeah.
Yeah, because things like those Goldstone modes would be very difficult to find.
Right. But yeah, we were not looking for this, and actually we didn't find what we were looking for. One of the results was the confirmation of one of the conjectures that initially motivated the experiment, just not having evidence of it.
So
all right, so
I think we had an unusually long discussion. So it's time for us. I hope it was really productive. That's my impression. And
yes.
And thank you for this talk. And it's time for us to thank our speaker. So thank you very much, Eun-Ah.
Thank you.